For years, one assumption sat at the center of the global semiconductor race: extreme ultraviolet lithography, often shortened to EUV. The process that uses ultra-short wavelength light to etch the smallest transistor patterns ever made onto silicon, was something China simply could not obtain. Not because of a lack of intelligence or engineering talent, but because the technology was locked behind a single company, ASML, of the Netherlands, and protected by the most aggressive export control regime in modern history. As a result, EUV was treated as the final and immovable bottleneck. Without it, China could not manufacture the most advanced chips. And without those chips, it could not compete at the highest levels of artificial intelligence, advanced computing, or modern weapon systems. But that assumption is now under pressure because, according to a detailed investigation by Reuters, a high-security laboratory in Shenzhen has quietly assembled a prototype EUV lithography system. The machine was reportedly completed in early 2025 and is now undergoing testing. It occupies nearly an entire factory floor and has successfully generated extreme ultraviolet light at the required 13.5 nanometer wavelength. It has not yet produced working chips. But it exists, and it is operational in a limited sense. And that fact alone forces a reassessment of timelines that many experts once believed were measured in decades rather than years. This is not a rumor or an internet exaggeration. Reuters describes a system built by a team that includes former engineers from ASML, the Dutch company that holds the global monopoly on EUV technology. Even more striking is the level of secrecy surrounding the project. Engineers were reportedly issued identification cards under false names and instructed to use aliases even inside the facility. The project is classified under national security, with strict compartmentalization and isolation between teams, a structure far removed from normal commercial research and development. To understand why this matters, it is important to understand what EUV actually represents. EUV lithography is not simply another machine in a factory. It is the mechanism that allows chipmakers to print the smallest circuit patterns humanity has ever produced. The process uses extreme ultraviolet light to draw billions of microscopic features onto silicon wafers, features so small they are measured in single-digit nanometers. The smaller the features, the more transistors can be packed into a chip, and the more powerful and energy-efficient that chip becomes. This is the technology that enables the most advanced processors designed by companies like NVIDIA, AMD, Apple, and Qualcomm, and manufactured by foundries such as TSMC, Samsung, and Intel. In fact, every modern AI system, whether trained by companies like OpenAI, Google, Anthropic, or Meta, or deployed in data centers, smartphones, and military platforms, ultimately depends on chips fabricated using EUV lithography. Without EUV, the performance, scale, and efficiency that define today's artificial intelligence simply would not exist. Until now, only ASML has been able to build EUV machines at all. Each one costs hundreds of millions of dollars, weighs roughly 180 tons, and integrates hundreds of thousands of ultra-precise components sourced across multiple countries. ASML built its first EUV prototypes in the early 2000s. But it took nearly 2 decades and billions of euros before the technology reached commercial viability in 2019. Long and painful development timeline is precisely why many analysts believed China would need 20 to 30 years to replicate EUV, even with massive investment. Western governments built policy around that belief. Starting in 2018, the United States pressured the Netherlands to block ASML from selling EUV machines to China. Then, in 2022, those restrictions expanded into sweeping export controls, targeting not just EUV, but also deep ultraviolet lithography tools, software, and advanced components. The goal was simple: slow China's semiconductor progress long enough to preserve a permanent technological lead. However, the Shenzhen prototype challenges the idea that this lead can be frozen indefinitely. At the same time, it is critical to understand what China has not yet achieved. The machine has not produced functional chips, and that distinction matters more than any headline. Generating EUV light is the first major hurdle, but it is not the finish line. Turning that light into a production-ready system capable of printing chips reliably with high yields and economic throughput is a far more complex challenge. This is where many experienced engineers urge caution. In advanced engineering, the first 80% of progress often happens quickly. The final 20% takes longer than everything that came before it. Early breakthroughs are exciting and visible, but the final integration phase is slow, frustrating, and rarely makes headlines. It is during this stage that teams uncover subtle issues involving contamination, vibration, thermal drift, optics, degradation, and yield collapse, problems that can take years to resolve. ASML itself lived through this reality. The company demonstrated EUV light sources years before the technology was economically viable. The problem was never making EUV light, but making enough of it reliably without destroying the optics or contaminating the system. Earlier approaches such as laser-produced discharge plasma were abandoned because they could not deliver sufficient power for commercial manufacturing. ASML ultimately committed to laser-produced plasma because it was the only approach that could scale, even though it introduced extreme engineering complexity. This is why some analysts remain skeptical that China will be producing large volumes of EUV-based chips in the near term. A light source that works in principle is not the same as a light source that works at scale. Underpowered or unreliable EUV sources would severely limit throughput, making mass production economically unviable, even if the rest of the system functions. Yet, skepticism about timelines should not be confused with disbelief in capability. China has repeatedly demonstrated that when faced with constraints, it does not stop, it adapts. In shipbuilding, China launched more military vessels in a single year than the United States built over an entire decade. In manufacturing, a vast majority of the world's advanced technical products are fabricated in China. In many cases, Western companies willingly transferred knowledge and process expertise in exchange for lower production costs, effectively training future competitors to save short-term expenses. China's talent pipeline further complicates assumptions. Western university science and engineering programs often have more Chinese students than local ones. Every major technology company employs large numbers of Chinese engineers, many of whom eventually return home. When Western governments cut research funding, cancel programs, or lay off engineers after projects are completed, that expertise does not disappear. It migrates. Non-disclosure agreements are difficult to enforce across borders, and institutional knowledge does not vanish simply because paperwork says it should. This is why the involvement of former ASML engineers in the Shenzhen project is so significant. EUV is not something that can be copied from blueprints alone. Even ASML engineers have said that reverse engineering EUV would be nearly impossible, even with full drawings and a physical machine. And yet, similar claims were once made about electric vehicles, before Chinese manufacturers like BYD proved otherwise. According to Reuters, China's EUV effort relied not only on human expertise, but also on salvaged hardware. Components from older ASML machines were reportedly acquired through secondary markets and auctions, along with parts from Nikon and Canon systems. This does not mean China has recreated the entire supply chain, but it does mean enough components were gathered to assemble a prototype capable of testing, learning, and iteration. The structure of the program itself reflects its strategic importance. Reuters describes it as China's version of the Manhattan Project. Huawei reportedly plays a central coordinating role across chip design, fabrication equipment, manufacturing, and final product integration. Employees assigned to semiconductor teams reportedly sleep on site with phone access restricted and teams isolated from one another. This level of secrecy is inefficient for normal commercial development, but highly effective for national missions where speed and information containment matter more than comfort. The most serious technical obstacle that remains is optics. ASML's EUV mirrors produced primarily by Germany's Carl Zeiss are among the most precise objects ever manufactured. They must maintain atomic-level smoothness while operating in a harsh EUV environment under vacuum. Even a tiny defect can destroy yields. Chinese researchers have reportedly made progress integrating EUV light into the optical system. But significant refinement is still required, and many engineers believe this will be the longest phase to mature. Even so, the timeline has already shifted. Analysts once believed China would not reach this stage until the mid-2030s. Now, working prototypes exist with internal targets around 2028 and more realistic estimates closer to 2030, and that compression matters. The broader implication is not that China has won the semiconductor race, but that permanent containment may be unrealistic. EUV was the last major bottleneck China had not visibly crossed. If it falls, the logic of long-term hardware dominance weakens. The semiconductor industry has always been globally distributed, and no single country has ever controlled every layer from raw materials to finished chips. What makes this moment different is the possibility that China could become the first country to hold near-complete end-to-end control across the entire stack. The Shenzhen prototype does not signal an endpoint. It signals a transition. It shows that, under sustained pressure, China is willing to trade elegance for brute force, efficiency for sovereignty, and time for scale. Even if commercialization takes longer than optimists expect, the direction is no longer in doubt. The question is no longer whether China can approach the frontier, it is how long the remaining distance will take and whether this becomes a leapfrog moment that allows China to dominate the next phase of computing altogether. Thank you so much for watching all the way to the end. If you enjoyed this deep dive, please smash that like button, share your thoughts in the comments below, and don't forget to subscribe and turn on notifications so you'll never miss a future update. We've got a lot more exciting tech stories coming your way. Until next time, stay curious, stay inspired, and we'll see you in the next video. Goodbye.